10 structures, one of them shouldn't exist. Number 10. Boss Great Wall. Mass, not length, is what makes this one different. Most entries on this list earned their place by being unexpectedly long or unexpectedly empty. The Boss Great Wall earned its place by being the heaviest coherent structure ever measured. In 2016, Heidi Lietzen at the Instituto de Astrofísica de Canarias published the discovery using data from the Baryon Oscillation Spectroscopic Survey. That survey measured precise redshifts for over 1 million galaxies, producing a three-dimensional density map far sharper than anything available a decade earlier. The wall was not found by eyeballing a scatter plot. It was extracted by systematic density algorithms that flagged an unmistakable overdensity spanning roughly 1 billion light-years. Inside that billion light-year region sit at least 830 galaxies, organized into 4 superclusters connected by a web of filaments. The estimated total mass exceeds 10,000 times the mass of the Milky Way. Picture our entire galaxy, every star, every planet, every cloud of gas it contains. Then multiply that by 10,000 and compress it into one connected wall. That is what the survey found at a redshift of 0.47, roughly 4.5 billion years in the past. Lietzen tested whether the wall was gravitationally bound. She measured galaxy velocities within the structure and compared them to the local expansion rate. The densest cores are bound. They will survive as permanent clusters long after the filaments connecting them dissolve. The outer bridges are more fragile. So some will thin and break as cosmic expansion wins the tug of war. The boss. Great Wall is not one monolithic slab. It is a complex of gravitationally bound islands linked by temporary bridges of galaxies. Even defining it conservatively, stripping away the fragile filaments and counting only the bound cores, the structure is still far more massive than anything standard simulations typically produce in that volume of space. The models say the universe should not pack that much matter into one connected feature this recently in cosmic history. The data says it did. Number 9. South Pole Wall. It was like discovering a mountain range behind a billboard you had been driving past your entire life. For decades, an enormous arc of galaxies curved through the southern sky and nobody saw it. Not because it was far away. Because it was hiding behind the Milky Way. In July 2020, Daniel Palmeride at the University of Paris-Saclay and R. Brent Tully at the University of Hawaii published a paper that finally revealed it. The structure spans at least 1.4 billion light-years. Its densest region sits only 500 million light-years from Earth. That makes it one of the closest giant cosmic features ever found. It had been invisible because of the zone of avoidance. The zone of avoidance is the band of sky blocked by the disk of our own galaxy. Dust, gas, and billions of foreground stars create a wall of clutter that blinds optical telescopes. Even infrared surveys struggle to see through it. The southern celestial pole sits right in that blind spot. Palmeride and Tully used a different approach entirely. Instead of trying to photograph galaxies through the clutter, they used galaxy velocities from the Cosmic Flows 3 catalog. That catalog records how fast galaxies move relative to us. By mapping those motions, they could infer where hidden mass concentrations must be pulling galaxies toward them, even when the galaxies themselves were invisible behind all that galactic dust. The technique revealed a sweeping wall connecting known clusters in a long arc across the far southern sky. Some of those clusters had been cataloged individually for years. Nobody had connected them into a single feature until Palmeride and Tully drew the full map. Think about that for a moment. A structure 1.4 billion light-years long was sitting 500 million light-years from Earth, and we had no idea it was there. So if a wall that size can hide in our own cosmic backyard, what else is lurking behind the Milky Way that we have never seen? Future radio telescopes and the James Webb Space Telescope can peer through parts of the zone of avoidance. What they find there could quietly redraw the large-scale map of everything we thought we understood about our local universe. Number 8. Sloan Great Wall. When the CFA2 Great Wall was discovered in 1989, it held the record for the largest known structure in the universe. That record lasted 14 years. On October 20th, 2003, J. Richard Gott III and Mario Jurich at Princeton published a map built from the Sloan Digital Sky Survey. They had plotted hundreds of thousands of galaxies by redshift and position. What emerged was a filament 1.37 billion light-years long. The CFA2 Great Wall could fit inside it nearly 3 times over. The wall sits about 1 billion light-years from Earth. It threads through the constellations Leo, Coma Berenices, and Virgo and connects several massive superclusters into a single chain. The richest concentration is a supercluster cataloged as SCL-126, a dense knot anchoring the surrounding filaments like a boulder sitting in a fast-moving river. The question with structures this size is always the same. Is it one connected object or several smaller ones that happen to line up from our vantage point? In 2011, a follow-up study argued it might be 3 separate structures aligned along our sight line. If true, the problem shrinks. But even 3 aligned walls of that size would be unusual. Alignments that meet do not appear often in simulations, and that raises its own set of questions. The wall also works as a laboratory for studying how gravity and expansion compete. Astronomers measure how galaxies inside it move relative to each other. The densest cores appear to be collapsing inward under their own gravity. The outer regions are expanding along with everything else. That tug of war is exactly what you would expect from a structure caught in the act of deciding whether to hold together or slowly come apart. One object or 3, the Sloan Great Wall forces a choice. If it is one continuous filament, our timeline for how quickly gravity can assemble structures needs adjusting. If it is 3 objects that happen to align, the probability of that alignment still demands an explanation. Neither option is comfortable for the standard model. Number 7. Huge Large Quasar Group, 73 quasars, not 7. Not 17. 73 supermassive black holes, each one tearing apart surrounding gas so violently it outshines its entire host galaxy, all packed into a single region 4 billion light-years across. That number alone should stop you. Roger Clowes at the University of Central Lancashire announced the discovery in January 2013. His team had been mining the Sloan Digital Sky Survey catalog, using a linking algorithm to identify clusters of quasars separated by less than a certain angular distance. So, what emerged in the constellation? Leo was a grouping so dense and so large that it exceeded the theoretical smoothness limit by a factor of 3. That limit exists for a reason. Cosmology rests on the idea that if you zoom out far enough, the universe looks the same in every direction. The smoothness scale is roughly 1.2 billion light-years. Beyond that, matter should distribute itself evenly. The Huge Large Quasar Group spans 4 billion light-years at its longest axis. It does not care about the limit. Clowes ran Monte Carlo simulations to estimate the probability of 73 quasars clumping this tightly by accident. The odds came back very low, but critics argued the linking algorithm was too generous. Change the linking distance by a small amount and the group fragments into several smaller clusters that look unremarkable. Others ran cosmological simulations and occasionally produced similar-sized groupings as rare fluctuations. Neither side backed down. What made the result harder to dismiss is that the huge LQG sits in the same general region as the Clowes-Campusano group, 2 massive quasar concentrations in the same patch of sky at comparable distances. One clump can be debated, 2 of them sitting side by side is a pattern that nobody has been able to explain away. Number 6. Boots Void. Fly through it at the speed of light, and for 330 million years you would see nothing. No galaxies, no clusters, no faint smudges of distant starlight, just blackness in every direction. Stretching further, there's the distance from here to the Virgo cluster. The Boots void was discovered in 1981, and it immediately felt wrong. When astronomers mapped that patch of sky, they expected to find thousands of galaxies. What they found was a hole. A handful of galaxies sit inside where hundreds should be normal. The cosmic web is built from dense filaments separated by voids. Everybody knows that, but those voids are typically smaller and not nearly this clean. The Booties void looks scrubbed. It looks almost deliberate, which is exactly why it bothers physicists. Nothing deliberate happened. Something else did, and we do not fully know what. Astronomers went back with the Keck telescope and the Very Large Telescope to see if the void was hiding faint galaxies below the original detection threshold. They scanned the emptiest patches for anything dim. A few faint objects turned up, nowhere near enough to explain the emptiness. One explanation is that the void started as a rare deep dip in the primordial density field, a spot where the initial conditions of the universe happened to be unusually smooth. Matter flowed outward into surrounding filaments and never returned. Another possibility is that dark matter or gravity behave differently in large underdense regions, allowing voids to clear out faster than models predict. The Euclid Space Telescope is designed to test exactly these kinds of questions. It will map void statistics across a much larger volume than any previous survey. If many voids the size of Booties exist, our density predictions need serious revision. If Booties remains the only one this empty, then it is a single, enormous anomaly that the universe produced once and never repeated. Number 5. CFA2 Great Wall. The idea was almost absurdly simple. Measure the redshift of every galaxy you can find. Convert those redshifts to distances. Plot the dots. In 1989, Margaret Geller and John Huckra at the Harvard-Smithsonian Center for Astrophysics finished plotting their dots. What they saw on the screen stopped them cold. A wall, not a random scatter, not a gentle gradient. A sharp, coherent filament of galaxies stretching 500 million light-years long, 300 million light-years wide, and only 15 million light-years thick. A cosmic sheet of matter so flat it looked engineered. Nobody had seen anything like it before. The wall links the Coma cluster and the Hercules cluster into a single sprawling feature. That moment rewired how astronomers understood the universe. The cosmos was not a smooth fog of galaxies drifting randomly through space. It was organized into sheets and walls and filaments, separated by enormous voids. The cosmic web was real, and the CFA2 Great Wall was the first time anyone had actually seen it. The discovery changed what telescopes looked for. Surveys scaled up dramatically. Simulations got slower and more detailed because the models suddenly had to reproduce what the sky was actually showing. One important lesson came from studying how these walls age. They are not solid, permanent objects. Gravity pulls galaxies into filaments, but cosmic expansion pulls them apart on the largest scales. These sheets are often temporary, impressive today, diluted in a few billion years, gone in 10. That distinction matters deeply. If a feature is transient, ordinary gravity and a lucky formation history explain it. If a feature is permanent and larger than expected, then something is missing from the physics. The CFA2 Great Wall taught astronomers to ask that question about every giant structure that came after it, and the structures that came after it kept getting bigger. Number 4. Clowes-Campusano Large Quasar Group. Finding one quasar is noteworthy. Finding 34 of them packed into a single region 2 billion light-years across is like spotting dozens of lighthouses clustered along the same 100 miles of empty coastline. Something built that arrangement. The question is what? Quasars are active supermassive black holes tearing apart gas and radiating so fiercely they outshine everything else in their galaxy. They are rare precisely because the conditions that create them are extreme and short-lived. The Clowes-Campusano group sits at a redshift around 1.28, which means we see it as it was roughly 9 billion years ago. At that distance and that size, the standard model says it should not exist. Researchers checked every obvious flaw. They remeasured redshifts to confirm the objects were truly at the same distance and not just scattered along the line of sight. They ran Monte Carlo simulations and found the chance of a random alignment extremely low. They checked for gravitational lensing that could make a background quasar appear in the wrong place. Lensing can move one or two objects. It cannot relocate 34. The group also lies disturbingly close to the huge large quasar group. So that proximity makes the problem worse, not better. One giant clump might be a statistical fluke in a big enough universe. Two of them sitting near each other in the same region of sky starts to look like the universe is far lumpier at early times than the standard model predicts. The Dark Energy Spectroscopic Instrument is building deeper quasar maps right now. Whether the Clowes-Campusano group survives that level of scrutiny or dissolves under sharper data will settle the argument. But if it survives, the consequences ripple outward through every assumption we make about how uniformly matter was distributed in the young universe. Number 3. Big Ring. Most cosmic structures look like messy webs or tangled filaments. This one looked like someone had drawn a circle in the sky. On January 10, 2024, Satsik, Alexia Lopez announced her second impossible find. Using the same magnesium absorption technique that revealed the giant arc, she and her team traced a near-perfect ring in three-dimensional space. It spans 1.3 billion light-years across. Its circumference stretches 4 billion light-years. That puts it right at the boundary where the universe is supposed to stop producing coherent structure. The ring is strange for reasons beyond its size. Baryonic acoustic oscillations, pressure waves from the early universe that left circular imprints on how matter is distributed, could in theory create ring shapes, but those imprints should be roughly spherical. The big ring is too elongated and too flat to match that explanation cleanly. Some astronomers suspect it is a sampling artifact, so a trick of how quasar sight lines are distributed across the sky. Others point out that Lopez found it in the same general region as the giant arc, at similar redshifts and similar distances. Two anomalous structures in the same patch of sky at the same cosmic distance is harder to dismiss as coincidence than either one alone. The more exotic proposals include cosmic strings threading through the early universe and leaving circular scars in the distribution of matter. Another idea invokes conformal cyclic cosmology, where traces of a previous cosmic cycle survive into this one and leave large-scale geometric imprints. Neither idea is proven, but the ring refuses to disappear from the data, and every reanalysis so far has kept it intact. Number 2. Giant Arc. SOAT's Alexia Lopez was not looking for the largest structure ever found in quasar absorption data. She was a doctoral student mapping magnesium absorption lines in Sloan survey spectra, tracing clouds of gas that sit between us and distant quasars. The technique is indirect. You do not photograph galaxies. You read the shadows in the light of objects behind them. What emerged from that shadow map was a chain of galaxies stretching 3.3 billion light-years across. If you could see it in the night sky, it would span roughly 60 full moons from end to end. The arc sits 9.2 billion light-years away and covers about 1/15 of the radius of the entire observable universe. Let that scale sink in. One single structure spanning 1/15 of everything we can see. Lopez and her team ran the statistics. The probability of that pattern appearing by random chance came back at only a few in 10,000. That number is what separates a curious blip from a genuine crisis for cosmological models. Some groups ran simulations and produced vaguely similar patterns. Others tried the same simulations and could not reproduce anything close. A rival analysis claimed the statistics were overstated, that random alignments can masquerade as structure if you search long enough through large data sets. Then came fresh, independent data sets that reproduced the signal anyway, and the disagreement hardened into a genuine scientific fight that continues to this day. The explanations run from mundane to radical. Rare patches in the early universe where matter clumped more aggressively than average. Unknown physics that nudged filaments into alignment long before galaxies existed. Thin defects in space-time called cosmic strings that could have seeded the pattern billions of years ago. Each idea makes distinct predictions about what future surveys should find. The Rubin Observatory and Euclid Space Telescope will deliver those surveys within the next few years. Until they do, the giant arc remains a 3.3 billion light-year question mark hanging in the southern sky. Number 1. Hercules-Corona Borealis Great Wall. Lay a ruler across the entire observable universe. This wall would cover more than a third of it. Light would need 10 billion years just to cross from one end to the other. 10 billion years. The universe itself is only 13.8 billion years old. Astronomers first noticed something wrong in 2013. Gamma-ray bursts, the brightest explosions in the cosmos, kept appearing crowded into one patch of sky. That should not happen. These bursts come from collapsing stars scattered across billions of light years. They should look random when you plot them on a map. They did not. Follow-up teams used redshifts and galaxy surveys to trace the source. What they found was a chain of galaxies and clusters stretching across a region so vast it breaks a foundational rule of cosmology. That rule says the universe should look roughly the same in every direction once you zoom out past about 1.2 billion light-years. Beyond that scale, everything should blur into bland uniformity. This wall ignores that rule by a factor of 8. There is not enough time since the Big Bang for gravity alone to weave something this large. 14 billion years is simply not enough thread. Think of it this way. If you started building this structure at the moment of the Big Bang and worked at the speed of light, you would still not be finished. That is what makes this wall so deeply uncomfortable for physics. Some scientists argue the pattern comes from how we sample the sky, that the gamma-ray burst catalog has blind spots that create false clusters in certain directions. Fair objection, but the signal shows up across multiple independent surveys using completely different methods. Gamma-ray bursts, galaxy redshifts, absorption line mapping, all of them point to an overdense region at redshifts around 1.8. That consistency across independent datasets is what turned curiosity into alarm. A planned space mission called Theseus could settle the argument by mapping gamma-ray bursts with far greater sky coverage and sensitivity than any previous catalog. If Theseus confirms the overdensity, then the largest structure in the observable universe is real, and it is 8 times larger than physics says it should be. If Theseus does not confirm it, then we need to understand how 3 independent observational methods all pointed to the same false positive. Either outcome rewrites a chapter in how we understand the universe at its largest and oldest scales.